And if we look at our introductory statement, assume a hypothetical postsynaptic neuron, oh my Lord, has 3 presynaptic inputs. All right, here is my postsynaptic neuron. And there is one presynaptic neuron. Here is another presynaptic neuron. And here is another presynaptic neuron. And X, Y, and Z. All right, here's X, and here is Y, and here is Z. Also, assume presynaptic neuron Z is excitatory. All right, let's put a plus there. So that's where we are. Now, if presynaptic neuron X is stimulated, the postsynaptic cell membrane becomes slightly hyperpolarized. What kind of a synapse is involved between presynaptic neuron X and this postsynaptic neuron? And so, what would our answer be?
B.
And that would be inhibitory. Exactly. We can make the postsynaptic membrane. Well, how can we make any neuron hyperpolarized? We can open the potassium channels, and the concentration of potassium on the outside is already positive, but I'm going to add more positive to it, so it's going to mean that it's going to take a lot more influx of sodium to change my polarity. So whenever you hyperpolarize a membrane, you're going to have a neurotransmitter that's going to open potassium channels and make the concentration of potassium outside the cell membrane a lot higher than normal. Now then, if we did, well, wait a minute, what we say, what kind of synapse at X, it is inhibitory, so we put a negative there. Then if presynaptic neuron Z, here, is repetitively stimulated very rapidly, what change would you expect to occur in the postsynaptic membrane? And you chose which one there? The answer is C. Exactly. It is temporal summation. In other words, we've got a single synapse involved, but it is stimulated repeatedly. Yes. So, we got that one. Those two. Number 3, assume a hypothetical postsynaptic neuron has 3. All right, we've already done that. When presynaptic neuron, okay, let's erase this now. We don't know for sure about that. When presynaptic neuron X and Y are stimulated simultaneously, the postsynaptic neuron reaches threshold and undergoes an action potential. So, let's put a positive there. Now then, when presynaptic neuron X and Z, what, X and Z? Am I right? Are stimulated simultaneously, there's no change in the potential of the postsynaptic. No change. So if there's no change, it's got to be inhibitory. Now, so we put a negative there. What can you tell about presynaptic neuron Y and Z?
Nothing.
Anything?
Do you have extras of those?
I'm sorry?
Do you have any extras of those papers? Because I didn't get one Wednesday. That wasn't here.
Anybody else need one of these? All right. What can I tell about Y and Z?
Y is excitatory and Z is inhibitory.
That's exactly right. Exactly right. That is exactly right. These two, this one's excitatory, and this one right here is inhibitory. This one cancels out this until it's in this negative. This one and this one together is the same, so it has to be excitatory. If you want to be able to do some mental gymnastics, when you do that. Okay. Be sure your name is on that. Be sure you leave it with me. Otherwise, you won't get your reward. And so now we're going to look at the basic unit, the fundamental structural unit of the nervous system, and the reflex arc. We did not do the reflex arc. Okay. Well, this is the spinal cord. Well, we're going to put right here a representation of a cross-section of the spinal cord. So, we're going to start like this. And we're going to leave one side of it off. So what we have here is this. Well, why didn't I put this on? That's perfect. Maybe. Yes. So I've put this in and I've cut it off right over here. So, right in here is going to be the gray matter of the cord, like so. Then this right here is the white matter. And it's white because of oligodendrocytes. And the white matter is divided into columns. And we have 3 columns. We have the dorsal white columns. We have the lateral white columns. And we have the ventral white columns, but they're sometimes called the anterior white columns. So right here is the dorsal white columns. The lateral white columns are on the side, and the ventral white columns are here. The gray matter, which makes up the interior of the spinal cord, is gray because there's no mile. But it is divided into horns. Well, I better put gray matter and horns. Well, we have the dorsal horns. We have the lateral horns. And we have the ventral horns of the gray matter. These are points of reference. This is illustrated in your book. Now then, we're going to put out here, and let's just pretend this is going to be the skin. And right here, we have receptors. Receptors are nerve endings, or they are special cells that respond to a stimulus. Now we're dealing with a reflex arc. And for the reflex arc to function, we've got to have a stimulus. And then we've got to have a receptor that responds to that stimulus. Receptors are specialized for a particular stimulus. Well, I'm going to have then these receptors will form a dendrite that will bring the impulse into the cord via a spinal nerve. And remember, we have 31 pair of them. And it enters the cord via what's referred to as the dorsal root. and the dorsal root has a swelling that contains the cell body of this sensory neuron, and that's called a ganglion. So we have the dorsal root and we have the dorsal root ganglion. Here is a spinal nerve. Here is a spinal nerve. And here is the dorsal root. Here is the ventral root. And here's the dorsal root ganglion. Be sure you see that in lab. Now, I'm going to have an axon that exits the ganglion and enters the cord itself. And now it's going to make a connection to a motor neuron. The motor neuron is going to have an axon that exits via the ventral root. Then out through the spinal nerve. And it will end in an axon terminal, and that axon terminal will be resting on an effector, which is muscle and there's three categories. It can be skeletal muscle, it can be cardiac muscle, or it can be smooth muscle. Or it can rest on a gland and bring about secretion. These are called effectors. So, the simplest of all of your reflexes, the most simple of all of them, is referred to as a monosynaptic reflex arc. A monosynaptic reflex arc consists of receptors that respond to a stimulus. Then I have to have a sensory neuron to bring it into the CNS. So my third component is a sensory neuron, which is input into the CNS. Then I have to have a synapse where one neuron connects to another. Then I have to have a motor neuron which is going to be my output. Then I'm going to have an effector, which is going to be muscle or gland. And then I'm going to have a response. That is the components of a reflex arc. And this is the simplest of all of them. Now we're going to look at this one, but then we're going to look at a very, very, very complex reflex arc. But we want to be aware of the components first and the simplicity that we're going to build on. Now, over on page 450, at the bottom of the page is an illustration of what's called a stretch reflex, and this is a monosynaptic reflex arc. If we go through this, then the receptor is a specialized cell called a spindle or muscle spindle. It responds to stretching the muscle. There's a sensory neuron there in red. It enters the dorsal root where the cell body is. It enters the gray matter of the cord and then makes a synapse with the neuron indicated in black. Now that neuron cell body is located in the ventral horn of the gray matter. Then I have an axon coming out that's going to go to skeletal muscle. It's going to make a myoneural junction in this case, and I'm going to get a response. So, that's monosynaptic. Now, I'm going to set the individual up here on this table. And the doctor's going to come in and take this little rubber hammer, and he's going to tap the patellar tendon right here. Well, when he does, that's going to stretch the quadriceps, which in turn is going to stimulate those muscle spindles, those receptors. Well, that's going to send in an impulse up to the spinal cord, and then it's going to make a connection with a motor neuron that's going to send an impulse out to the muscle fibers here, causing a response. Now, you know, you think that's not a big deal at all. What's that going to tell that old man? Well, now, that lower motor neuron that's indicated there in black, we've got to understand that there are many other motor neurons connected to that one. Not just that one sensory neuron and one motor neuron. There's one sensory, yes, but there are many, 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 many other connections from other neurons connected to that black one. For example, I've known this doctor for all my life. and I'm going to fool him. So when he taps my patellar tendon here, I'm going to send down inhibitory impulses to that lower motor neuron, and I'm not going to let that motor neuron send an impulse, and I'm not going to give them a response. So I can do that. It's a voluntary thing. It originates up here, it goes down to that lower motor neuron, and it inhibits, it hyperpolarizes that lower motor neuron, and when he taps it, nothing happens. Or, I also have the option of sending down via another neuron to that same motor neuron, and in essence, I can excite it, and when he taps it, I can do that. You see? So that lower motor neuron, that black one there, has many, many, many other neurons connecting to it. Well, if you have something wrong, if you've got damage done to a spinal cord, if you've been in some sort of accident, and you have possibly done some damage to your spinal cord, can I send down then impulses from up here to down there? No. So that's going to modify the response that the doctor is checking. So he's looking for any modification of the knee-jerk response to see if there's damage done to the spine. So are we together? You see the purpose. Okay. Now, we're going to get really excited, and we're going to look at polysynaptic. Polysynaptic reflex, or what does it? This one is called monosynaptic because there's only one synapse right here. Just one. Polysynaptic means there are many, but it's going to be the same. There's going to be a stimulus, receptor, sensory neuron input, but instead of one synapse, there's going to be many synapses. Now, it's going to take a second for me to find it. Ah, not so much. Let's look over on page 519. There's a table. All right, we're going to take the very first item in that table, and it's called the lateral spinal thalamic tract. This whole table deals with principal ascending sensory pathways. In other words, sensory information is coming in, and it's going to go up to the brain, and then we're going to get to decide what the response is going to be. So, the first of these is the lateral spinal thalamic pathway. Well, what does that mean? All right, here's the core. When it says lateral, that tells you that this tract or these neurons, are located in the lateral white columns. Spinothalamic tells you that this tract originates in the spinal cord and terminates in the thalamus. Now, we haven't mentioned the thalamus, but we will. So, this is the first polysynaptic reflex arc we're going to be dealing with. Now, the sensations, pain and temperature. So, this is sensory information dealing with pain and temperature, hot and cold. If I have damage done to these ascending tracts, I'm going to lose the sensation of pain and temperature. All right. Now, it says location of neuron cell bodies. We got first order, second order, and third order. First order, dorsal root ganglia, axons enter the CNS at the dorsal root. Well, Lord of mercy. If you'll turn over to the very next page. This is on page 520. 520. Look at the one on the right-hand side at the very bottom. Well, those were angels. All right, we've got pain and temperature. You see the red neuron coming in and making an immediate connection with the one that's illustrated in white. Now look what happens to the white neuron. It crosses over immediately and ascends the opposite side. Ascends the opposite side all the way up to the brain, to the thalamus of the brain. It'll make a connection there to the black neuron, which will take it to the cerebral cortex, and now you're aware of it. So, now, pain and temperature over here comes in over here, but then crosses over and goes up this side. And then there in the thalamus, it'll go to this cerebral cortex. So pain and temperature over here is interpreted over here. So if I have damage done to my spinal cord on this side, I lose pain and temperature over here. If I have damage done to this side, I lose pain and temperature over here. Are we together? Yes. Opposite side because it crosses in the cord. Yes. It goes all the way up to the cerebral cortex. Now it's not labeled. Oh yeah, it is. There in the cerebral cortex. It says primary sensory cortex. Well, now turn to page 486. Now keep that space where you are, but also turn to page 486, and you see a lateral view of the brain. Look at the blue area, the parietal lobe, and look what it says. The primary sensory cortex. All right, that's where that third neuron is going to innervate. That's the area that you're going to become aware of pain and temperature. You have to go through 3 neurons to get it up to the cerebral cortex. Once it gets there, you're now aware of it. Until it gets there, you're not aware. Now, going back to where we were, on 520. On page 520, at the very top there, where it shows the primary sensory area, do you see those body parts and how they're distorted? That's called a homunculus. That's an interesting word. I'm sure it is Latin, and I don't know what it means. I'll declare. We ought to find out, shouldn't
It means little human, like
it
myself.
means what?
Little human,
Little human. All right.
like myself.
Good for you. Amen. Little human. And that's where we interpret pain and temperature for various areas of the body. Look how big the hand is. What does that tell you? That there's a lot of area of the cerebral cortex devoted to the interpretation of pain and temperature in the hand. Not so much elsewhere in the body, but a lot of it's in the hand. So, my cerebral cortex is divided off into areas for interpretation of these senses by various parts of the body. The lateral spinal thalamic tract, you want to be aware of. You want to be aware that it crosses in the core. You want to be aware that it takes 3 neurons to get it up to the cerebral cortex. Have we completed the reflex arc? No. All we've done several synapses. We haven't done any of this. So we have so far just dealt with this particular tract and these pain and temperature sensations. All right. Now, well, now I've already lost my place. No, we did. You need to go back to page 519. On page 519, go back to that table. Go down to where it says fasciculus gracilis and fasciculus cunatus. Sensations involved: proprioception and fine touch, ventral pressure and vibration from the inferior half of the body, and then the same sensations from the superior part. Proprioception. What is that? Proprioception. Can you reach down and touch your foot without looking? Do you know where your foot is? Right now. Yes. That's proprioception. The ability to know your body and its relationship to the external environment. If you didn't know where your foot was, would you have a problem walking? Obviously. And if you get into the health sciences and you have to deal with somebody with a spinal cord injury, and especially this particular tract, do you see the implications? Well, we're going to take just a couple of these tracts, but there's a whole bunch of them. This particular tract, the fasciculus cunatus and gracilis, deals with proprioception and fine touch. If somebody reaches over and touches you, company. Now, to make it easy, let's go back to this illustration on page 521. On 521, there is an illustration on the left-hand side, starting at the bottom. Again, this is the fasciculus cuneatus and gracilis. Look, we've got a red neuron. That's the first one. The first order sensory neuron number 1. It comes in, but look, it goes up the same side, all the way up to the medulla. It crosses over in the medulla, goes to the thalamus, and then from the thalamus it goes to the primary sensory area of the cerebral cortex, which is the parietal lobe. So, fine touch over here. Fine touch. Proprioception. Comes in and goes up this side. It crosses in the medulla, goes up to the thalamus, and then from the thalamus to the cerebral cortex. Now, if I have damage done to this side of my spinal cord, am I going to have proprioception over here? Yes, because it comes in and goes up this side. But, am I going to have pain and temperature over here? No, because it comes in and goes up this side. Are we together?
I have a quick question. You know when your limbs go to sleep and they tingle? Is that part of this probe?
Yes, but that's because of the deficiency of oxygen available for the impulse to occur.
Okay, so if you had damage, you would not feel the tingle?
The damage in that case, when we have the problem, it's deficiency of oxygen available for the establishment of the impulse.
Okay, that's actually very helpful. So when my foot falls asleep, if I take in more oxygen,
You need to move a little bit, switch to so the blood vessel. That's why. Okay, when you go to bed at night, do you ever flop around a little bit? You just don't come in there quiet and wake up the next morning in the same position. You move around during the night. Well, why do you move around? Why does a cow die when it flops down and can't get up? Oh, you hadn't thought about that? Well, whenever you flop down and you put pressure on that tissue, what happens to blood flow? Oh my goodness! If you're going to the health sciences and you happen to go to a senior citizen home, why do they say you move them around? Because if you don't, pressure is going to cut off the blood supply to various areas, pressure points, and the tissue is going to die, and they're going to get bed sores. Exactly. And so, because they don't move, well, during the night, when you're flopping down, you move to ensure you get good blood flow through all the tissues. You don't want the tissues to go without oxygen very long, or they're going to die. Now see, you knew all that. You just need to think. Right? So you don't want to get bed sores on your butt. You want to move around a little bit. But being very serious, that's what happens in rest homes And that's why these individuals, it's very important that they are moved if they can't move themselves. Otherwise, the tissue is going to rot, then it's going to slough off, and then you're going to get gangrene, and then they're going to die. What brought all this on?
Things happening on one side and traveling up and going to
There
the
you
other
go.
side. So I was just concerned. I was asking about a limb falling asleep, and
So now we're going to keep in mind the fasciculus cunatus and gracilis and the lateral spinal thalamic tract. So this, sit down. Well, just about. Oh my God, the weekend's almost here. Those are the two ascending tracts. You want to be aware of them. We haven't even got to descending tracts. So come Monday, we're going to start with my impulses in the primary sensory area of the cerebral cortex. Leave your stuff up here if you want credit for this.
Okay, so, who was the girl that Lisa or whatever she sits right
Well,
there?
the pain and
She had
temperature
the
comes up
question
from
that we
the
needed to ask for the quiz, and I don't know what the
That's the
question was.
reason.
I know that it was about question 3 on the online quiz.
Whoa, all right.
But I don't remember what the actual question was. She wrote it down in her notebook.
if I see the questions, which I should have on my phone, hold on, let me get
I have
this.
them real quick. I can just pull them up.